Hello and welcome back to another LeetCode video. Today we're looking at LeetCode 2048, next greater numerical balanced number. And I think this problem is exciting not only because 2048 is the power of 2, but also because it combines two LeetCode problems into one. And one, as we're going to see, is to build the power set, and two is going to build all combinations of digits. Well, but I'm getting ahead of myself, so let's read the problem description to see what we are dealing with here. So it starts with an introduction. Well, the integer x is numerically balanced if for every digit d in the number x, there are exactly d occurrences of that digit in x. Given an integer n, return the smallest numerical balanced number strictly greater than n. Well, what does that mean? Well, let's look at the examples and we'll see. If we're given the number 1, the output is 22. And that is because 22 is numerically balanced, since 2 appears exactly twice. And 1 would also be numerically balanced, but we're looking for the next number that is strictly greater than 1. And for the input 1, that is the output 22. Here's another number where we get an input of 1000. And the next numerically balanced number that is greater than 1000 is 1333. And you can see here 1333 is numerically balanced because 1 appears only once, the 3 appears exactly 3 times, and that makes it numerically balanced, and it's up to us to find, if there are any smaller ones. But in this example, we know that this is the smallest numerically balanced number, strictly greater than 1000. And the final example, we get the number 3000. And the output is 3133. So what you can see here is that, we can combine numerically balanced numbers into a new numerically balanced number as long as the properties are preserved, meaning we cannot have more than 3 threes, we cannot have less than 3 threes. But we can arrange the digits in there. So even though 133 is a numerically balanced number, it's not larger than 3000. But if we rearrange the digits, we can get to a number that's larger than 3000. So that is where, building all the different combinations of the digits comes in. And that's something that we're going to do. Now, this problem has a special property where the input number is smaller or equal than 10 to the 6th. And if you think about it, there is also an upper limit for the largest numerically balanced number. And that is if you combine, what you could say is, you could say that we can have some numerically balanced numbers. Actually, let's enumerate them. Let's write them down. So 1 would be 1, right? 2 would be 1. And 333 would be 1. 4444. The same with the 5s. 6 6s would be 1. 7 7s. That's 7. That's 7. And 9 9s. Right? So those are all numerically balanced numbers. Let me see if I got the count right. Right. So that's 7. That is, there's an 8 missing here. And the 6s, yes, I did count correct. Cool. So those are kind of the numerically balanced numbers that consist of only one type of digit, right? And now we can combine them. And if we concatenate all of them, maybe in reversed order, that would give us the largest possible balanced number, right? It would start with 3 9s, then 9 9s, 8 8s, etc. So that would be the largest number. The smallest one would be just the 1. So if we think about, generating numbers, we already know that everything is going to be bounded by the maximum number. So we can already say that our approach is going to be constant time and also, time and also space, simply because there's an upper limit to the numbers that we're going to build. And for practical purposes, also n is going to be constrained by, I guess LeetCode, right? But since we have a hard upper bound, everything suddenly becomes constant. Cool. So how could we approach this? Well, I think The first step would be, we should generate all the possible combinations of these numbers, because those are all possible inputs where we can try to rearrange the digits to find the number that is strictly greater than n, but also the smallest number that is strictly greater than n and that is balanced. So we're going to need a little bit of a helper function to generate all of those candidates. And then we're also going to need a function that will take a number like this and compute the smallest rearrangement of the digit that is larger than n. And then finally we will have a loop over all of our, I guess, I would call them seeds. And actually, let's start to implement this. You'll see. Generate seeds. And what this does, well, we start with this. Those are our initial seeds where we only use one type of digit, but we need to compute all possible combinations. And that's the same as computing the power set. I don't know if you remember how to do that. Initial seeds, numbers with only one digit. Sorry, balanced numbers, right? Balanced numbers with only one seed, with only one digit in it. Next, we need to build compute all combinations of balanced numbers that are also balanced numbers. And we can do that with generating the power set. And this is probably something good to remember how to do that. I forget which LeetCode problem that is, but there's one where you need to build the power set. And it's actually quite simple. If you do that a couple of times, then you will, well, I guess it'll just be muscle memory. So we're going to start with an empty set. So our power set contains the empty set, and I'm just representing this as an empty list. Next, we're going to iterate over all of the numbers that we have, all of our balanced numbers. And I just use the variable e for element. And well, now what we do is we will combine it with every element that we already have in our power set. So for I in range length of our power set. And well, now we need to combine it. So we need to add a new element, or I guess a new set, right? And that would be the set. That would be the power set at position I. And remember, in a power set, there are only sets. So we take the set and we combine it with a new, with a new set that has our element E in it. And then we just append that to the power set. That's all we need to do here. So you can imagine in the beginning, we combine all the elements in nums with the empty set. Well, actually, it works slightly different. So what it does is first we combine the empty set with the number 1, right? In the next step, we combine, well, this gives us the empty set and the set with the number num. In the next step, we combine the empty set with the number 2, because that's our next nums, our next element. And we also combine the element, the set with the element 1 with 2. So that will give us the empty set, the set with 1, set with 2, and the set with 1 and 2. And so it will subsequently build up the entire power set by combining all the existing ones with the next element. So now the next step would be to combine the set with the number 3 with all of those sets that we have in here and append that to our power set. So that's the way that works. And well, now we can do some optimization here. And when I implemented this with Python, we're currently dealing with strings, but when we want to compare numbers later, and they can become super large, if we combine all of these numbers into one, then convert them to int, we get a problem. So for practical purposes of this problem, I'm going to define a max digits and a max values constant. And I'm just going to, well, we know the max is 10 to the power of 6. And let's leave it some room so that maybe the answer is somewhere 10 to the 7 There's still a number that's a larger balanced number than n that can be 10 to the 6. And we also define a max value. And that is just going to be 10 to the power of, oh, where are my, I changed my keyboard layout. Still trying to get used to that. And we just multiplied it to the max digits, right? So what we can do now here is we can do a little bit of optimization here. So one would be, well, if the length of my number is larger than max digits, right? We're not going to be interested in this. We're just going to continue. So effectively, you know, it would throw away the 9, right? That's what would that do. Now, next, we could perform some more filtering on all of the numbers in our power set. You know, in the worst case, our power set contains, how much is it? 10 to the power of 9, or 2 to the power of 9 different values. So 512, but because we just excluded the 9, that's only going to be 256 different values. However, a lot of them are still going to be larger than our max value. So let's set up a new set. We call this the seed set. And we will just take out all the elements of the power set that are smaller than max value, right? And we're going to also sort all of these sets inside our power sets. That will come in handy when we start to compare the seed values to our target value n plus 1, right? So let's do that. So for set in power set, we're just going to, well, combine all the sets that we have. Remember, we have the elements of power set are going to be sets, and they contain strings, so we can combine them like so. And we're going to sort them so that smaller digits always come in front of larger digits. And now we perform another little check. If seed, because remember we have the empty set in here, so we don't want to convert that into a number. We have to add that as a constraint when we filter. So if seed and the length of seed is smaller than max digits, then we know that this is a candidate number. Then we're just going to append this value as an integer to our seed set. Right, so, and yeah, because of this optimization, we can be sure that we can actually convert it to int. If you just joined all of these numbers, try to convert it to int, Python would give you an error. Right, so this is building the seeds, right? So in our main part of the code, we'll just have a function that calls that seeds, so we get all the seeds. And our result, what is our result going to be? Well, in the worst case, it's going to be the largest number in seeds. And at the end, we're going to return the result. And in between, well, we need to do something here, right? Well, and what do we need to do? Well, we need to iterate over all of the seed numbers and see if we can use the digits in them to combine them to a number that is larger than n, but as close to n as possible. So we will iterate over the elements in seeds, right? And, well, we could perform a quick check if we wanted to here. If result is equal to n plus 1, now we're just going to break. It means we've already found we found a number that is larger than n by 1, and it's our possible result, so we're done, right? So we found n plus 1 as a balanced number. Otherwise, well, what do we do otherwise? Well, if there are two cases now, so the seed could be larger than n or it could be smaller than n. Now, if the seed number is larger than n, what does that mean? Well, remember, because we sorted the numbers that we put into our seeds array, that means if a number from the seed array, we should call it seed, makes it better to read. So if the seed number is already larger than n, there's no way we're going to find a smaller combination of digits of the digits in seed that is closer to n. That's the reason why we performed the sorting here in this place. So if that is the case, the best we can do is we can hope that our seed number is now closer 2n than the previous result. So we'll just update our result like so. Well, otherwise, what do we do otherwise? Else, now we know that seed is actually larger than n. So, that seed is smaller than n or equal to n. And if the combination of digits is already smaller, that means we could maybe reverse it, and maybe that's a larger number. And if it is, then we found a number that we could try to rearrange the digits to get closer to n. So that's exactly what we'll do. So we'll compute, I guess, seed. Well, yeah, let's just rearrange our seeds. So what we'll do is we'll make seed be the string version of seed, but then we're going to reverse it. So we're just reversing all of the digits in seed. And that is now the largest number that we can build using the digits in seed. And normally when you have a trailing 0 in a number, you can't just reverse it and cast it back to int. But because we never have any zeros in our initial numbers, we're not going to have any zeros in our seeds here as well. So now seed is another candidate. And now we check if seed is larger than n. Only then we can try to rearrange the digits to find a value that is closer. So what we'll do now is we'll extract the digits, and we'll just do the following. Int, well, I guess int digit, or digit in string of seed, right? So that's how we get now all of the digits in a list. And what we'll do now is, well, we have to implement another helper function here. Find closest to target. And we'll pass in the digits here, and we'll pass in a bunch of other stuff there in a second. And what should we pass in? Well, let me just complete this real quick. So candidate equals the function that we call. And just to finish this logic, if this candidate that we get back, and that should be the closest value to our target value, if candidate is larger than our candidate than n, then it's a potential candidate to be our result, right? So again, we take the minimum. I see some typos. Result. That's actually that's okay. Right, and that would complete the whole logic of our main code. But now coming back to how do we implement our find closest to targets function. And that is a similar problem that we already saw in other LeetCode problems, where you need to find a number that is close to something or find a target number using available digits. So we pass in the digits, we pass in the ones that we already picked, and we'll use a set to indicate the indices of the numbers that we picked from digits. And what else? Well, we will append I guess the current value and our min target value. That's the minimum value that we want to get to. And our current value is going to be 0. Our min target is going to be n plus 1, right? We don't want to find a closest target that is n. It has to be strictly greater than our input value n, right? Strictly greater than n. So yeah, what is left to do? Well, we just have to compute that. So, well, the result is just going to be, by default, an infinitely large number. So that in the end, we're guaranteed to, well, if we do this minimum comparison, we don't want to have a default value of 0. So an initialized result was infinity. At the end of the method, we want to return the result. And in between, well, we have to have a base case. When do we terminate our recursion? Because this is going to be a recursive implementation. So if the length of digits is the length of how many digits we picked, then we know we're done. And now we just need to check, if the current value is larger or equal than minimum to target, well, then we can return, the minimum target, right? Otherwise, we're going to return float infinity. And we can simplify that a little bit like so. There you go. So only when the current value is larger or equal than min target, then we're going to update our result to min target inside this function, right? So maybe I should call res as result, not to be confused with the result down here. Right, and the other case is, well, we have to iterate over the digits, right? And and that makes only sense if the current value is smaller than max value. Because if max value actually, because if current value is already if current value is larger than max value, let me think. Actually, that's not true. We should probably just do an else here. Yeah, should be an else, I think. So now we just iterate over all of the digits. And we iterate over all of them. And if we already picked that, we're just going to continue. Oh, 1 second. Sorry, I had an interruption. I'm not going to edit this. Much work. Anyway, so if we already picked the digit at position I, well, then we're not going to pick it again. So we're just going to continue. And otherwise, well, we're going to add this index to our picked set. We have to do a recursive call. And after, we have to remove I again. Like so. Now, well, how do we do the recursive call? Well, we will update our result, right? So we have another candidate here that comes from our recursive call. And to our current value, we have to add the digit. But also we have to multiply it by 10, right? Because we are picking, well, we're building up the number. So we have to multiply the number by 10 and add the least significant digit, and min target stays the same. And now we just have to compute, you know, maybe candidate was a better, closer result. So what we'll do is we'll say res is min of res and candidate. There you go. So that is the whole thing. First, we compute the power set that gives us all possible combinations of digits that we could use to try to build a number that is strictly greater than n, and where the number is also a numerically balanced number. That's why we generate the seeds using the power set. We have an optimization here to not include numbers that are too large. That'll help us to basically do integer comparisons along the way. Otherwise, we'd have to do string comparisons, just much slower. And yeah, more effort to write. And next, what we do is, well, we iterate over all of the candidates that we generated. By candidates, I mean all of the digit combinations that we could use to try to find a number larger and close to n. So we iterate over them, and we call our function that helps us to build all different combinations of digits. And yeah, and then returns the value that we built using all of the digits that's the closest to our target value. So let's see. I'm just going to run the code and see if I made any typos anywhere. And looks like I did. There's an unmatched closing bracket. So, and for e in nums, there's a loop error when we build the power set. Next, seed append. So seeds is the array, and we need to return the seeds. The seed is the value. Right. And well, we could probably do if not s continue. So we filter out the empty set right up here. And then we just check the length of the seed. Okay, let's run this again. So now we're getting the wrong answer. Why is that? So we're outputting zeros here. So that is not great. How do we get any zeros inside of our code? That should never ever happen, right? Times equals 10 plus digit. So we never add a 0. Oh, current val times 10 plus digit. And we iterate over the digits in digits. Oh, is it that we add a 0 digit anywhere? We pass in the digit. That's the first parameter. That's the ones we picked. So it means that somewhere we end up picking, well, if we do current value times 10 plus digit, so maybe digit is 0 anywhere. So what I'm going to do to debug this, I'm just going to print the digits that we have here. Right, digits. So we get the correct number of digits. So that is all nice. Okay. And so it's not in here. So where do we go wrong? So it must be, I guess, somewhere in our base case. So the number of pick digits is the same as the ones that are available. That is our base case. Now we check if our current value is larger or equal than our min target value. If that is the case, then we return a result. Now when we find the candidate, so this looks clean as well, doesn't it? So now let's look at this. So we iterate with I over all of the digits. If I is a pick digit, then we're going to ignore it. And we're going to add I to our picked and remove it here. Then we do the recursive call here. Current value times 10. It's minimum. I think that's also good. So let's see what happens. What's our next value? Do we actually have digits that are not, well, that are 0? Digit and digit. So let's see if we introduce the error somewhere here. Even there we don't. So I don't see any zeros in here. Nowhere. Even when we scroll down, there are no zeros there. So next val is never 0. So that is also good. So now I'm going to say, well, if the current value is larger or equal min target, then let's print the candidate that we have here. See if that contains the zeros that we don't want. And now we get lots of candidate. Res is a candidate. Oh, well, why do I say min target? That's nonsense, right? So it should be res is the current value. All right. Well, I'm glad we went into this debugging session. All right. So it passes the test cases. And let's see now if it passes all of the tests. And it does. Happy days. So yeah. Just to reiterate, everything is constant space and constant time, simply because A, the constraints, n has an upper bound. But if n didn't have an upper bound, you still have an upper bound that is imposed by the fact that the number that we're looking for is going to be numerically balanced. And since there's an upper limit for what's the largest numerically balanced number is, well, everything is constant space and constant time, because we could point out an upper bound that is a high number that is smaller than the largest number that we can build. if actually n was potentially larger than this, and maybe we should return -1 if it doesn't exist. In that case, what we would do, we would simply check if result is smaller or equal to n, return -1. So that would be the way to deal with the case that n would be larger than n to the power 6. And it would keep the space and time complexity the same as well. Now, we did 2 tricks. We generated the power set with all the possible combinations of digits that we can have, all the possible, I guess, smallest numerically balanced numbers. And then we use those to rearrange the digits to try to find a number that is as close as possible to target using our find closest to target a recursive helper function. Right, and this concludes this video.